Okay, so the webinar is now live streaming on YouTube. I will make it start the webinar in the next 30 seconds or 1 minute when the once the clock hits 3 p.m.
Rohit-san, you will be asking me to share the screen, right?
Yeah, I'll
Okay.
prompt you when
Yeah, okay.
when your involvement is required.
Yeah.
Okay, I'm making the webinar live now. I will begin now. Good afternoon, everyone. Thanks for joining us for today's session on BMS application and inverter system functional safety concepts for xEVs. This session is brought to you by the team at Commercial Vehicle Forum and Two-Wheeler, Three-Wheeler and EV Forum, or as we are more popularly known, TWF and CVF. And we have partnered with Renesas Electronics India Private Limited for this session. My name is Rohit Dewan, and I'm the Portfolio Director at CVF and TWF. While most of you are already aware, but for some of the new attendees who are joining us, just to give you a very quick introduction, CVF and TWF are India's premium C-level commercial vehicle, two-wheeler, three-wheeler, and EV industry events. And before we start today's session, I am really pleased to inform you that we've launched Transport Utsav. Transport Utsav, as the name suggests, is a complete festival of transport that brings together truck owners and fleets who will be attending, alongside solution providers such as trucks, tires, lubricants, finance, insurance, engine, truck technology, and component companies who will be showcasing their products. We are organizing this exhibition in association with Nalagarh Truck Operators Union, which is Asia's biggest transport union with around 4 to 5,000 members. The two-day exhibition will be taking place on 3rd and 4th of March 2023 in Baddi. We will in fact have participation from over 10,000 visitors here, so do join us for the same. Next, moving on to the agenda for today's session, I will be kicking off the proceedings of this live session with a short introduction. Post the introduction, our speaker for the day, Srinivas-san, will deliver a brief presentation, followed by a few audience questions towards the end. Your active participation is important to make this session a success. Right now, we have you all in listen-only mode. But here is how you can interact with us. You can ask us questions. At the bottom of the screen, you will see a Q&A box. Please feel free to send us your questions in the Q&A box. We will take those questions in the Q&A segment of today's session. You can also choose to upvote these questions. This will help us in addressing the most burning topics. Do note this webinar is available on demand, and we have this session streaming live on YouTube as well. Moreover, anyone who has registered for the session will also receive a recording post the completion of the session. Apart from that, I request you to share your insights in the feedback form that will open as soon as you exit the session. If there's something else you're interested in learning more, please feel free to reach out to us. So before we begin today's session, I wanted to now take the time to especially thank our partner, Renesas Electronics India Private Limited, for supporting this session. Just to give you a very quick introduction, Renesas designs and manufactures microcontrollers, analog, power, and sensor devices for automotive applications. To bring out the full capabilities of devices and make the designer's life easy, they build solutions using their winning combinations of products, ICs. For the demanding applications in electric vehicles, they have built solutions for inverters and battery management systems. In today's fast-paced and short design cycle, building everything from scratch in conventional method is time-consuming. Hence, Renesas has built models and software to support design engineers to bring out solutions quicker to market. Renesas has made complete hardware solution of these important blocks in EV for two-wheeler as well as for four-wheeler. Their BMS application model and software solution reduces research and development effort by providing sample application models that estimates state of charge and state of health. Optimization of these safety functions requires time-consuming, system-dependent safety analysis and evaluation. For xEV inverters, Renesas can help customers shorten development time by supporting functional safety at the system level. Now, to shed more light on this, I would like to introduce the speaker for the day. Mr. Srinivas Krishna Menon is presently working as Senior Manager at Automotive New Business Creation Division at Renesas for the past 6 years. He has over 17 years of experience in field application engineering and sales in the semiconductor industry. Prior to this, for 13 years, he had been working as a design engineer in medical electronics and in the consumer electronics domain with multinational majors in these fields. In terms of his education, he is a postgraduate in information technology and graduated with a BE in electronics and communication, both from the University of Mysore. He has done his diploma in management from AIMA. Thank you so much for joining us today, Srinivasan. Over to you to take it forward.
Thank you, Rohit. Thanks for giving the brief introduction about the seminar as well as about myself. I shall be sharing my screen now.
Please go ahead.
So can you see my screen now?
I can't see your screen. I'm sorry.
Not yet?
No.
Hope now you start seeing the screen.
Yeah, I'm seeing the screen.
Okay. Sure. Can you see the main page?
Yeah, you can go ahead.
Okay. So this is, thank you for attending this, taking your time and attending this webinar. So good afternoon, all the participants in this webinar. So this, I will talk about today about the Renesas BMS application and inverter system functional safety concepts for the xEV vehicles. So today's agenda is the market trend, like the xEV product portfolio that Renesas has, and what are the winning combos with Renesas. So this is a special terminology that we use for the set of products that we promote a particular application. And then we take you to the automotive BMS application models and software. Renesas has spent a lot of resources in building these models and software for the proper the quick design to market functionality for the esteemed customers of Renesas. And as a last point, but very important one, is the functional safety concepts for the EV inverter system. So we all know there are functional safety concepts available for the gasoline vehicles, for the diesel vehicles, but the same thing is applicable to EV in a little more detail because there is a lot more electronics now into the vehicle. So functional safety concepts is even more important now. And then finally, we conclude with the summarizing the whole webinar today. So today I talk about the mega trends. So the mega trends is that from the need to the market change. So what does it mean is that there is a need always. The need is the mother of any invention. And then finally it becomes a requirement in the market, and then it starts changing the dynamics in the market. So the end user, the needs are basically environmental friendly products. Safety and security is topmost. And of course, the comfortable and convenient, the commuting is one of the important things that everybody aspire for. In terms of when it translates into technological innovation, the environmental friendliness, of course, is totally galvanized by the electrification of the automotive today with the efficient power management. And then it moves on from safety and security perspective. It becomes an automated vehicle with high performance processing built into each of the vehicles. And in terms of comfortable and convenience, it becomes more connected, secure, and safe. And of course, use of cloud for the navigation and also for a lot of information, sharing. And the last one, how the market changed with these two in the mind, with the user needs and the technological innovation subsequent to that. There is an 8-fold increase in the electric vehicles by 2025. That's what is estimated. And a 5x increase in the sensor content from the autonomous vehicles in terms of the levels, such as L2 to L4 to L5 vehicles. And then a 2-fold increase in the telematics installed in the vehicles by 2025. So telematics is catching up a lot because there is a lot more information to share as we automate and as we gather more and more information about the rider, the connectivity, and all of that. So this is basically the mega trends driving the market change. So now let us come to the market trend changes in the xEV. The market is clearly shifting towards the battery electric vehicles due to the technology evolution trends and environmental policies. A possible transition is for a fully hybrid electric vehicle prior to becoming completely battery electric vehicle seems to be likely in China kind of countries, but of course it can occur even in the EU, European market as well as in the US markets. So if you look at the trends that are changing, so we have compared 4 major geographies: the US, the Europe, the Japan, and the China. So in the US, you will find almost a 112% increase from the present value of market by 2,163K units all the way to 4,607K units. And this is by 2025. So this is almost 112% increase from the present condition. And when we move to EU market, it's even more higher, almost 161% increase we find in 2025. And in Japan market, we find 82%. And in China market, we find close to 128%. So anywhere between 100 to 200%, we find that the movement of the market is happening towards a completely battery electric vehicle, or at least to a fully hybrid electric vehicle, which is almost like an electric vehicle along with a gasoline engine or an IC engine. So this is the mega trend that is taking place, and this is the change in the market. And this is inevitable, and it is there, and it is good for us. So this is what is the message from this slide. When it comes to the xEV product portfolio, so what are the portfolio of products that Renesas has in terms of the broad and diversified Renesas product portfolio with highly competitive performance? Many of the products below are used in multiple times, means it is used in multiple numbers for various systems in a single automotive, in a single vehicle, or even inside the same system. For example, an inverter, it could be multiple products that we'll be using. That means what I mean to say is that the semiconductor content is increasing, and hence the complexity, and hence the need for more safe and secure electronics on board. In terms of scalable MCU family, so you find that in terms of a secure MCU family, you find that the MCU is all pervasive across all the products. And the best fit optimized power management basically is the PMIC, the power management IC, and then comes the intelligent power devices, which are basically high side drivers for high power switching on and off, and of course the gate drivers for switching the power MOSFETs or power IGBTs. And when it comes to the precision sensing, what Renesas offers is the battery management IC. We are going to cover it in much more detail as we move forward. The battery management ICs are very precise, so what Renesas has got, and it does a very accurate measurement of the SOC, SOH, as well as the cell voltages. And the battery current sensing is another important thing. From few milliamperes to few hundreds of ampere, it need to do with linearity. And then comes the sensor signal conditioner. There are a lot more sensors today: high current sensors, pressure sensors, the voltage sensors, the humidity sensor. There are many more sensors in the automotive today. So sensor signal conditioning becomes even more important to align the linearity and the variations with respect to temperature. And the unique analog in terms of CMIC, in terms of contactor driver, these contactor drivers are usually used in the battery switching. and the position sensor, accurate position sensing of the any moving system, including the motor position sensor, which is built inside the IPM motors, the BLDC motors. And when it comes to communication, what Renesas has is communication bridges, the BLE, the Bluetooth low energy products, Wi-Fi's, the optocouplers. So these are the major products that we can offer to the communication systems. And in terms of efficient power devices, of course, in the low voltage applications, we definitely need MOSFETs, and that too in tens of numbers mainly. And the IGBTs for the high voltage products, such as 100 volt to 400 volt to 800 volt, the products in the high voltage EV. And of course, the silicon carbide and gallium nitride products also we are bringing out for the electric vehicle market. So now let's look at the Renesas platform solution for the xEV product. So this is an all-pervasive slide. I like this slide. This slide brings out the broad portfolio of products, whatever I just described in the previous slide, with a lot more pictorial details here. The broad product portfolio serves as a wide range of automotive applications. It has got digital plus analog plus power plus the software. The last component is all the more important today because the products are more and more software intensive, and it requires a lot more safety and functional safety, the parameters built into it. And this is a fully integrated application-based optimized solutions. That is what we are going to discuss in the further slides. So the first one is the inverter. So Renesas has got, let's start from the motor. It has got the position sensor to identify the exact location of the rotor, and there is a functionally safe MCU. Then comes the power management ICs, and then here is the gate driver, which is the isolated gate driver for IGBTs and non-isolated gate drivers for the low voltage 48 volt applications. And here are the IGBTs modules and also the freewheeling rectifiers. And then comes the onboard charger. Renesas has both MCU and the power management IC. Then comes the gate driver and the IGBTs and MOSFETs for the power elements. And then is the major component, which is more safety required today, is the battery management system, the BMS. Renesas has the completely built board, which includes the battery management ICs themselves, which are analog front ends, and then the switching MOSFETs to do the balancing, and the MCUs, the ASIL qualified MCUs for the battery management ICs with the IPDs built in to switch the higher power. And of course, the other the emerging technologies such as BLE based the battery management systems, contactor drivers to drive the large power contactors, and the power management ICs for the MCUs. All of them is from the Renesas portfolio. And of course, the DC-DC will be needed from converting the high voltage system to the low voltage for your low voltage electronics, infotainment cluster, and telematics to run. So what we offer is the Renesas microcontroller, the power management ICs, the gate drivers, and the IGBTs or the MOSFETs are the final power delivery devices. So let's look at what's winning combo. So this is a very popular word Renesas has coined to attract your attention towards the winning combos. So what's winning combo? Winning combo is a system solution by combining our SoCs and MCUs along with analog and power devices, and including some of the sensors. So winning combo can help customers to accelerate the design, get to the market faster, and also reducing the customer's R&D effort by the reference design and turnkey solutions. So let's look at what do we offer, and I will explain why we are so particular about the winning combos and why do we request our customers to look at this. For example, if it is a simple, any simple system, it could be motor control, it could be battery management system, it could be instrument clusters, any one of them. So it's basically the complex system that we have listed here, A to D, the autonomous driving or ADAS systems, the electric vehicles, or the cockpit or human machine interface, or the vehicle controls and gateways. So all of them are quite complex today in terms of electronics, and they all require microcontrollers, SoCs, power management ICs, timing devices, the sensors, all of them. So this particular block diagram shows how they are embedded to each other to building a complete system, any one complete system as well. So it requires definitely power management, and there is a motor control IP running on the microcontroller, and there is an intense processing required in terms of calculations. And then finally, there is a sensing also is needed from the position, the current, the voltages, and the temperature. And then comes the actual actuation. To do that, you need the appropriate timing, of course, in terms of clocking the product, as well as the timing recognition and the noting the timings of the positions of this each of those rotor and things like that. And of course, finally, you need to show also the videos and display. So all of them have Renesas products in it, the key products, and all of them are combined and tested to make a complete set of solutions. As we see in the further slides, we will find a lot more important information I'm going to share in terms of how did we build these winning combos and how does it reduce the time to market for each of the customers. So here is the key advantage of the winning combos, and the winning combos for the xEV particularly. X stands for it could be hybrid, it could be fully hybrid, or it could be just the battery operated EVs. So differentiated approach is cost competitive, optimized system solution, and faster time to market. So these are the three things that we would like to bring in terms of the winning combos from the Renesas portfolio of products. So here the middle of it is the actual crux of it, the analog mixed with the digital, and of course the software and power. So the put together, it forms a complete winning combination. This gives the complete system solution, integrated digital plus analog plus power combos, and faster time to market that reduces the customer R&D efforts, because we have done a good amount of the R&D work already from our side, and we have been sharing you almost a year's experience and year's work that we have done already to the customer in terms of offering the winning combo solution. And best-in-class analog, the precision battery monitor systems, position sensing, low power, the Bluetooth low energy products, and power management devices. A scalable analog, scalable cell battery monitors, scalable functionality of the gate driver, flexible and configurable analog, efficient power devices, and high quality. This is one thing I just would like to stress. High quality means when we say less than 1 ppm return, this is the field return that Renesas expects or it is experiencing as of now. It's less than a parts per million for the 1 million devices that we sell. Less than one device comes back to us as an issue in the field. So that is a quality level we maintain, and the world-class methodology of manufacturing, and of course functional safety is built into each and every product. So automotive BMS applications, models and software. So this is one of the first, today I'm going to address two of the major winning combos that we just explained. The one will be the battery management system. The second one would be the electric inverter, the motor driver, and then the functional safety concepts of both of these. So let me come to some of the terminologies and the cell models. So what I mean to explain here is that, so before I just get into the modeling of the battery and the BMS and how did we build it and what software do we offer to our customers, I would like to give a very brief, just a brush up of some of the key terminologies to our valued viewers. One important thing that anywhere and everywhere I go in the market, everyone asks for SOC. This SOC calculation is basically very important for any battery management system. Let's understand what it is. SOC of a battery is defined as the ratio of its current capacity to the nominal capacity. Nominal capacity means the rated capacity of the battery to the current capacity. That is a ratio, it's a percentage. The nominal capacity is given by the manufacturer usually in his data sheet and represents the maximum amount of charge that can be stored in the battery in a good condition. So the current charge versus the maximum capacity that it can hold is basically the SOC. And when it comes to SOH, it is called a status of health. Today, we have seen multiple cases in India where there is a lot of fire accidents and other things happening on the EV. So this is becoming very important to look at the status of health of the battery. So over a period of time, the capacity to store energy in the battery starts fading, which all of us have experienced, whether it is laptop or our cell phones or the EV that is emerging. So but naturally, the status of health becomes more important. So SOH of a battery describes the difference between a battery being studied and a fresh battery and considering the cell aging. So it is defined as the ratio of maximum battery charge to its rated capacity. It is expressed as a percentage again. So let's understand how do we make an equivalent circuit of a battery. So the equivalent circuit of a battery is represented as the open circuit voltage, that is the battery's open circuit voltage with no stray elements or the built-in parasitics in it. And then when you do the real world modeling, you always get the series resistance in it, and also you get something called R1C1 effect. So this is basically the polarization effect in the charging and discharging process of a lithium-ion battery. So this is a simpler, but not so simple as well. A good approximation of a real-life lithium-ion cell or anything which is lithium-based. And this is the model that is being usually used to model the cell to calculate both the SOC as well as the SOH. So the OCV stands for open circuit voltage, and R1 and C1 are the polarization effect in the charging and discharging process of the lithium-ion battery, and R0 is the internal resistance of the battery. So what are the methods of measuring the SOC and SOH? There are basically three methods. They have, all of them have their own pros and cons, but we have selected the best one available today to do the modeling and also provide you the SOC and SOH. So the one of the easiest and one of the earliest method is the voltage method. In the voltage method, the voltage method converts a reading of the battery voltage to the equivalent SOC value by using the known discharge curve. So usually the discharge curve has been provided by the battery manufacturer. So that will be voltage versus the status of charge. It's kind of a lookup table, or it could be in terms of a graph or a curve as well. This will be given by the manufacturer. So you can look at the curve, and you can look at if this is the, let's say if it is 3.2 volt, so let's say it is 80% charge. If it is 3.1 volt, it is 40%. And if it is 3 volt or less, it could be like, less than 20%. So this could be an approximation. I'm just giving an example. So this is the one of the easiest method, and it's lookup table. But what happens is here you are not really factoring in the parasitic elements that are part of the real life battery models, which are R1, C1, and R0. So we are not really taking care of that. Even if we take care of that, the difference between the full charge to the lowest charge in a lithium-ion battery could show a very small dip in the voltage, which again confuses the algorithm whether what is the real charge, and with respect to temperature, this even complicates the matter. So what we measure the voltage when we cell is loaded, but what we are actually modeling is in the open circuit voltage. So this is one of the major drawbacks of this system. And we ignore the effect of the current that is moving also. When the current is flowing, naturally the voltages are different. So wide flat areas of the OCV, that is open circuit voltage curve, dilutes the accuracy of estimate. So this could be like, or sometimes it could be even very noisy. So you can the model can get confused. The another method is called current method. It is also called as Coulomb method or Coulomb counter. So this is one of the famous methods many of the manufacturers use. Coulomb counting is basically you are tracking the change of the current or the flow of current. This particular equation shows that SOC at any given point in time is basically SOC at T0, which is basically during the switch on time of the battery, which you are connecting to the load, and 1 by the total capacity, the nominal rated capacity of the battery, multiplied by the integral of the current measured with respect to time. So as you elapse the time, you keep integrating the total current that is flowing. If it is charging, it is plus, and if it is discharging, it is on the minus. But it gives in net what is the total current that has been consumed on the load side. So as you integrate this, you will get the total charge that has been moved out of the battery. So, but the issue is when you say, look at this component I measured, the I measured basically by the system, it has got many components in it. For example, I true, which is the true value, and the true current, that is what you are looking for. And there is a noise on top of it, and there is a bias current, and there are non-linearities in the system, and also there are leakage currents, and all of these put together, and there are etc. There could be few more components which you will find in a very detailed model. So all of these are actually adding up, and you are integrating it over a period of time. As you integrate it over a period of time, all of them gets integrated. So that means larger the time amount, for example, if you are running the vehicle continuously for 10 hours without switching off, then naturally these errors keep accumulating and summing up, and what you measure may be entirely wrong, or there should be a lot of measures being taken to avoid this kind of an error. So this is okay for a short period of operation when the initial conditions are known or can be frequently reset, subject to the drift due to the current sensors fluctuation, current sensors bias, incorrect capacity estimations, and other losses, and the second thing is the most important stuff is the error is unbounded. That means error can keep increasing, and it can keep getting integrated over a period of time. So uncertainty by error bound grows without limit over a period of time until you do the reset. The last method and one of the and the thing that Renesas uses is the model-based state estimators combine the voltage method and the current method using a cell model to do so to yield a better state of estimates. So the sequential probabilistic inference is the general framework. It is a statistical method being used that describes the model, the state estimator of the interest that we are looking for. The Kalman filter is being used. This is the statistical method that we are using. Is the algorithm to estimate the inner state of any dynamic system. It could be any dynamic system, which is one of the examples is the BMS. Compared to other estimation approaches, the Kalman filter automatically provides dynamic error bounds. That means the error is bounded. Unlike the Coulomb counter, the error is not unbounded, and it's the state estimates. Noise or sensor sites or the process site can be eliminated by tuning the covariance of values, and error remains bounded, which means not unbounded, even if your power of the system is you powered up the system for a longer time. So what we use is unscented Kalman filter. This gives more accurate results. So this is what we use in our model. And next comes so with this brief introduction of what we are going to show in the further slides, I'm showing up the battery management system that Renesas offers. So there is a large R&D effort that is required for any BMS application for writing the SOC and SOH by any of our customer. A high level of completion of software is needed in design phase at the same time to avoid the rework. So that means you need to do an accurate calculation of in the software so that you don't end up in reworking the whole software. So in the application software development, you will design the software, then you do the coding, and then it will go to the validation. So this is the standard V curve that any of the processes has got. The BMS application that is being followed. One second. The BMS application model and software solutions. Basically the R&D efforts by any sample application model software that estimates SOC and SOH. The sample simulating battery model we will provide that reduces the potential design rework through the simulation. Means you can do the simulation and you can understand the end result to a much higher accuracy than actually modeling it and then actually you ending up in a wrong result at the end of the day. So sample application software and drivers for both BMIC and IPDs. This also we will provide. This reduces the software programming efforts, and application notes covering everything from simulation on a PC to the actual execution on the board will also be provided by Renesas. So this is what we have been explaining till now. So this reduces the development rework by giving the application model and battery model. And then the actual coding, we also give you the application software and the driver software. And then validation. So both of these design and coding will be easy to start by application notes covering everything from simulation to PC on the PC to an execution on the actual board. And of course, validation will take place after we finish these two jobs. So the BMS application model and software runs on these two boards. The one is the multiple BMICs, that is battery management ICs with RH850 P1M reference board. So this is the actual hardware that we have. So here are those 5 BMICs, and here is the actual microcontroller. And then we also give a single cell. Suppose somebody does not want 5 of them, so you can also use a single cell BMS device. This kit will give you single. Also we come with the single core RH850 F1KM evaluation board for the lower cost. We also have RH850 P1M boards for the higher ASIL rated products requirement. So basically we have the battery management IC, the analog front end, and the microcontroller. So these are the 2 things which are needed. So here we have listed out the same thing. We have 2 microcontrollers that we have used in this modeling, and the software has been written for both of them. And one is an ASIL D device and the other one is an ASIL B. We use the power management IC to power up the microcontroller, and we use the battery management IC ISL 78714. This is a 14 cell IC monitor. And power device are these the high power switching devices, which are the IPDs we call, intelligent power devices. These are ones which you are used to make the contactor work or make any cooling system start. So all of these operations can be done through it. And of course the photocoupler for the isolation between the high voltage and the low voltage area. So all of these products are there on board the evaluation board. So here comes the modeling of the device and the the software for the SOC and SOH. So here we have the AFE ASL 78714 plus the microcontroller RH850P1M. So this is a simulation view of it. So both of these devices are there. So there is a measured the pack current, and there is measured pack voltage, and measured temperature, and measured cell voltage. So these the bottom three of them, the voltage, the temperature, and the actual measured cell voltage, pack voltage and the cell voltage, all these three parameters come from the ISL 78714, which is the battery management AFE. And the actual pack measure current, that is the whole pack's current measurement, comes from another current sensor. And all these four inputs, along with the user controls, go into the RH850P1M. And this is where the actual calculation of the model happens, and the estimated signals will come out of it. And also there is controls for the contactor to open and close in case of the on off in the normal case, or in case of an emergency as well. And there are fault flags that comes out as well. And the cell balancing enable input also comes out of this. So this is the major the block diagram of it. And then comes the driver and the applications Simulink. So these are the inputs that get into the actual Simulink model that we will provide to you. And the next one is the estimation of SOC and SOH starts here, with the Simulink model building in all the four inputs into it, and the estimated values coming out of the Simulink model. And then comes the estimation of SOC based on unscented Kalman filter. So unscented Kalman filter is most accurate one among the different variations available in the Kalman filter. For example, extended Kalman filter, non-linear Kalman filters, all of them. So basically the first block estimates the capacity. The UKF gives more accurate and faster conversions. We use it for our SOC estimation. And here is the UKF. So we will briefly describe what is this UKF does. So this is the Simulink model. The UKF estimates the SOC, the U1, which is the battery, the voltage across R1 and C1, if you recall the battery model, and then the R0, which is the series resistance, and R1 and C1 value. So the voltage across R1 and C1 is the U1, and the actual values of R1 and C1, all four of them will be, in fact, including the SOC, all five of them will be calculated by the UKF. And here is the sample application model. So what I explained in the pieces in the previous slides, all of those are put together over here, including the user interface, the GUI, and then of course these inputs go into this goes into the models, and then it goes into this the actual hardware that I shown you already, and then it goes to through a contactor, it goes into the actual cell, right? And the basic load is the charge discharge, which can be motor control, or it could be any other load in the EV. The sample application model estimates the battery status and the battery parameters from current, voltage, and temperature. So this is the actual simulation model that runs in the microcontroller and gives the output over here. So this is the fundamental crux of the sample application model that we provide to our customers. And here is the estimation of battery status and the parameter. So this is basically giving the actual versus the estimated. For example, SOC. So this is the yellow color shows the estimated value, and the blue color shows the real value. Okay, actually, if you see what's happening on the battery, that will be real, and what is estimated by the Kalman filter will be the yellow in the graph. So similarly, the yellow remains over here as well. This is the U1, which is the voltage across R1 and C1, and here is the CQ, the capacity of the battery, and then comes the R0 value, and it is almost constant across, and the R1 value, that is estimated versus real, and C1 value. So the R1, C1, and R0 are the stray elements inside the battery, which are not physically available, but they are part of the model, and the other things are the actual SOC that is being calculated. So this is the difference between the actual versus the simulated. So it is so accurate that almost all the time it follows the same trace. So finally, what you need is SOC, and that's what is being calculated with so much high accuracy. So here is the actual system that we utilized, APC, the control real-time simulator reference board, and it controls the real-time simulator and reference board and displays the result. And then comes the real-time simulator itself, that simulates the battery model in real time, outputs the shunt output shunt voltage and the thermistor voltage of the pack, current based on the simulation result, receives the relay control signals from the reference board and controls the relay model. The actual reference board that is over here, which we have shown in the earlier model as well, it measures the cell voltage, pack current, and the thermistor voltages and controls the relay as well. The actual cell simulator is over here, which is output cell voltage based on simulation results of a real-time simulator. It measures the cell current and sends the real-time simulator data. So what development tools that we used in this development and what customer would also need is the C code IDE, which is Green Hills software. We call Green Hills Multi, and the C compiler, which is again Green Hills software, and the model-based design tools, which is MathWorks tools, MATLAB, Simulink, Simscape, and Simscape Electrical and Control System Toolbox. In terms of the toolbox to generate the source code from the sample application model, you need MATLOAD coder, Simulink coder, and embedded coder. The OpenSSL is Win32 OpenSSL. So these are the basic softwares that we have utilized. So this is what we give to the customer. So in my previous slide, I end on the BMS, that what we deliver to our customer. And now I take you quickly to the development and the functional safety concepts for the xEV inverter system. So here is the inverter block diagram, that is a reference design. This is a high voltage inverter reference design. So this is the block which I explained in my previous slide as well. So this is the rated voltage of this device is that it can take in its battery plus terminal is 410 volt and with 500 ampere peak current. The output power is 40 kilowatt nominal continuous and 100 kilowatt peak. The output current is 200 ampere RMS and 500 ampere peak for 10 seconds. The input voltage can vary between 270 to 410 volts. The rotation speed can go up to 10,500 RPM. The total volume of this solution that you can see it over here is around 3.9 liter. The efficiency is up to 99% in the nominal loads. And the cooling is a water cooling with LLC mixture. The CAN interface is available. The motor control method is, many methods are available, space vector modulation, the space square wave control, and the discontinuous PWM method as well. So here is the block diagram of it. So this is the actual RH850C1M A2 is the actual microcontroller that creates that runs the entire motor control algorithm. Then is the driver ICs, the gate drivers, and then are the IGBT modules with built-in temperature sensors in it. And these IGBTs are AE4 and AE5. The AE5 is the one which is the newest and the latest in Renesas portfolio of IGBT products, which comes with the lowest VC SAT value, which is basically the loss factor in the IGBT. And we use isolated gate driver R2A25110 KSP. And through the current sensors, it goes to the motor, and the position feedback through the resolver digital circuit will come back. And this is also inside the microcontroller. This particular microcontroller runs on a hardware FOC, which means it is not a software FOC. The block inside the microcontroller runs the complete FOC without having any software intervention. That's the uniqueness of this microcontroller. And it associated with the power management IC from Renesas, and of course, photocoupler for isolated communication. Here is the practical results of it. This is the actual inverter that is 3.9 liter in size. This inverter is available for any customer to evaluate. And here is the actual evaluation system that we built up in Renesas. And here you will find the actual evaluation results as well. And this is being fitted in one of the cars, the sample cars, so that you can visit and you can drive this car. And here are the efficiency details. You will find at a nominal speed of 5,700 RPM and a torque of around 135 Newton, 80 to 100 Newton meter, you find almost 99% of the power efficiency. So at this page, the importance of efficiency is very high, because a 100 kilowatt inverter, even if 1% efficiency loss, which means almost 1 kilowatt you are losing, which is like an electric stove, which is otherwise used for heating purposes. So efficiency is of utmost importance. And here are the target scope of the products. Basically, this is what we talk about, the technical specification and also the functional safety. Easy to start system development with functional safety by using the reference work products from development phases, from concept to the end of design. So here is what we provide to you in terms of giving the total functional safety products, the work products that we provide. We provide the concept phase with item definition, hazard analysis and risk, and safety goals and functional safety concepts. On the part 4 of this, we provide part of it, product development at the system level, technical safety requirements, technical safety concepts, converted to the technical safety requirements, allocation to system functional design resources. So all of these, the functional safety work products will be provided by Renesas. And here is the flexible configuration of it. So this is, it can drive 2 different motors as well. The same design can drive 2 different motors as well. And also it can drive a boost and buck converter as well with 4 of the IGBTs. So this is a very flexible configuration. This design is quite, all pervasive. And here is the inside the pictures of this design. Here is the RH850 MCU, and you have the PMIC over here, and then the 6 isolated gate drivers, and then the 6 IGBTs and FRDs, which are mounted on the backside of it. Here is the battery input, and here is the 12 volt for the low level voltage functionality. So functional safety concept for this xEV inverter has been the evaluated and reviewed by the SGS Corporation of Japan, and so that is a certification that we have. So this is not just Renesas internal build product, but it is being verified and certified by the SGS Corporation of Japan as well. So here is a summary. Reduce the development time at customers to consider functional safety at the system level. Easy to start system development. xEV inverter system safety concept targeting up to ASIL C we will provide. Reference or work products reviewed by third-party organizations will be provided. Safety concept based on Renesas devices such as MCUs and PMICs, and the safety mechanisms will be shared. Enables development based on Renesas xEV inverter reference solution. This solution is a real product. It is not a paper solution. It is available for customers to evaluate. And flexible configuration of various inverter systems, single motor, dual motor, including buck boost, is possible to configure this product. So with that, I come to the summary page. Renesas is contributing to the acceleration of customers' development through our winning combination system solutions. Our BMS application model software solutions reduces the research and development time of the customer, which means easy to market. With SOCs and SOH the softwares and simulations being provided, it even makes much more life easier for our customers. Optimization of these safety function requires a time-consuming, system-dependent safety analysis and evaluation. For EV inverters, Renesas can help a customer shorten the development time by supporting functional safety at the system level. So that means we provide the system level support to you. So here are the resources in our website. You can log into www.renesas.com, and you will find a lot of these applications in it. You will find those system level block diagrams, the application supports, the downloads that are available in the Renesas website. You can look into the products. You can look at the applications wise. Also, you can look at the products in the secure portal of Renesas, wherein you can download upon a registration of yours. You can download a lot of resources and material from Renesas website. If you contact Renesas sales, we will upload specific application notes and other things which you require for your design, which are otherwise secure documents. And design support in terms of quality and packaging, frequently asked questions, user forums, and Renesas rules. All of these are the Renesas user sites and also the Renesas own resources that are powering the customers in terms of providing a quick help on the design debug. So with that, I come to the end of my presentation. Thank you for your time. Let me know if there are questions, and then I will try to answer as much as possible.
Srinivas-san, if you can just kill the share. There are a few questions we have received.
Yes.
Yeah. We received 4 or 5 questions, 5, 6 questions. I'll just go over them. So Mr. Balaji has asked, which ASIL class can Renesas meet in motor controller and BMS?
Okay, thank you. This is a very nice question, which most of my customers ask me this question. So ASIL is the functional safety level, and this is being now in India, more and more customers are asking for this. So ASIL levels, Renesas has right from just the AEC-Q 100 qualified products to all the way till ASIL D. So for a particular questions on the motor controller and BMS, we can provide products right from ASIL B to all the way to ASIL D. So it depends on customers' requirement and their safety goals they wanted to achieve, the OEM safety goals. Depending on that, Renesas has the products and portfolio of products that can be shared with the customer, and of course we are fully compliant with all the available and published ASIL grades.
Okay, great. So I'll move on to the next one. Ritul Shah has asked, how can you physically measure R1 and C1 in real time?
Yeah, it's basically an estimation. Basically, you need to provide the R1 and C1 values are available in the battery data sheet. They're typical and nominal values, and of course they may change a little bit over a period of time, or because of the tolerance of the battery. Any system comes with a tolerance, and that will help you. You can basically measure this with certain experiments even in your lab as well. So detailed discussions can be done later, but it is possible to measure, and the model also can estimate it with the initial values being provided to it.
Okay, great. Then Riya Shah asks, why only part 3 and 4 are covered for FUSA compliant inverter? Is the customer expected to take care of part 5 and 6?
Sorry, where is the question? Is it being shown on this one?
Yeah, in the Q&A box, it's number 3.
Okay, let me read it. Why only part 3 and 4 are covered for FUSA compliant inverter? Is the expectation that customer takes care of part 5 and 6 also? Yeah, correct. Because from the Renesas device perspective and getting into a little bit of the customer's area of some functional safety, we have created work products because we are experts on our product. We know what's inside the microcontroller, how did we build the functional safety, and how it need to be utilized by our end customer in building a completely functionally safe product. So this is our responsibility, and that is what we are taking care in the part 3 and 4, whereas part 5 and 6 are mostly towards the tier 1 or the end OEM to take care, in terms of that is more towards the entire product. So that will be taken care by the end OEMs, or the end user of the product. Initial parts are basically on the device side and the systems around the device. So that is what we provide to customers, because we are experts only on our device.
Okay, great. Somebody has asked anonymously why EKF estimation method is not considered for SOC estimation, which is much faster in estimation than UKF model and also having good accuracy.
Yeah, so this is being evaluated by our by our engineering team, and we found that the method that we have taken up, basically on the UKF method, the EKF method. Sorry, you are asking for UKF model, right? So yeah, this is being reviewed by our engineering team, and this is the decision they took, that this is the best to offer to the market, and that is more easier for customers to adopt. At the same time, it gives a very good accuracy as well. So that's our experience.
Okay. Then Mr. Viraj Kacharia asked, who would major players competing in India for MCUs inverters, either for two-wheeler or three-wheeler and four-wheelers? How do we compare capability versus ours?
Okay. Of course, there are competitors to us. We are not immune from any competition in the market. There are other multinational giants in the field in the competing with us, and we have quite a large share in India. For example, in the conventional EV is just maturing in the market, though there are a lot of designers that have come up, and there are a lot more customers. There are almost 700 EV companies in the India registered today. So, but still the volumes are less. But to prove my point, if you look at the existing IC engine products, we have more detailed products over there as well. For example, the instrument cluster, the electronic fuel injection system, the lighting control systems, the BCMs, all such modules. So we have very high appreciable share in all these markets. So that way, Renesas is kind of a leader in the existing India market for automotive, and we would like to continue the same even towards the EV, and that we are achieving as well.
Okay. Then Disha Patel asks, is Renesas working on high voltage BMS?
Yes, we are working on high voltage BMS. Basically, the high voltage BMS is the same BMS which is scaled up by stacking more and more cells. Like for example, when I named ISL 78714, or ISL 78716 that we are getting now, they can address 14 or 16 cells. Even if you assume 3.5 volt nominal, these devices can stack up to 30 such devices. So 30 devices in the sense 30 times 14. So times the voltage of the battery, like 3.5 volt or nominal. So you can build a appreciably very high voltage system. And these 78714s come with auto stacking. They recognize their position on the stack of the BMS devices. They are daisy chain connectable, which means you can connect from device to device. So let's say there are 10 devices in the daisy chain. So the first one becomes the master and the rest of them becomes the slave. And the first one collects all the data from the slaves and in turn it transmits to the microcontroller over SPI. There is a daisy chain proprietary algorithm that is running between the ISL 78714 AFEs. And that way you can stack up as high as 30 such devices times 14 times 3.5. So that's the kind of voltage you can build up. So it automatically means that, yes, we can build high voltage systems as well.
Okay, great. Then we've received another question from Satakatullah Sheikh Mohideen. What is the SOC and SOH accuracy achieved?
Okay, so I need to get the actual figures, but as I could describe in the graph that I just shared in one of all the Simulink model outputs. So we could achieve almost very close to the reality of the actual measured SOC versus the estimated SOC. So that way we achieve very high accuracy. But if you want to very precisely on the number, I can get back to you.
Then Abhijit V. Nair has asked whether the whole BMS system is ASIL compliant or only the chip is covered.
Okay. The BMS, of course, the chip need to be first compliant with ASIL, both analog front-end devices, which is complying up to ASIL D, and the microcontroller is also complying to ASIL D. If a customer wanted it to be in ASIL B, they can use a microcontroller of RH50 F1KM series, which is up to ASIL B. And if they wanted in up to ASIL D, they can use RH850 P1M series controllers. So the chip is of course compliant, and the board that is shown in the simulation is also ASIL compliant. But it all depends on how much customer want to adopt from my board. The customer may have a different form factor, they may have different features. The end OEM may be demanding so many other features, or they want to shed some of the features. And also the cost drives the ASIL compliancy. So of course, the ASIL requirement starts from the definition stage. It need to be defined from the concept stage all the way till the validation and completing the product. So ASIL is, of course, the answer to this question is the BMS and the microcontroller are compliant, and of course the board is also compliant. And it all depends on the end customers how much you want to adopt.
Okay. And Balaji has asked, can Renesas hardware and software solution suitable for active BMS product?
No, it's not usable for active BMS, which means the active balancing. No, it's passive balancing, because that is what is being very popular in the market. Of course, active BMS could be better in terms of environment and other things, but it is very expensive. So most of the manufacturers of semiconductor do not have this active BMS solution. Some of them have, but most of them will prefer passive balancing.
Okay. Mr. Pramod Patil has asked for battery cell monitoring. If one-off cycle may partially be damaged or may not charge as per state, then how BMS IC will take care the measure safety of batteries?
Okay, if a particular cell battery cell monitoring, if one cycle may partially damage one cell, it could be, I think it is one cell. If one of the cell may partially damage or may not be charged as per the state, and then how BMS IC will take it. Okay, so this IC comes with the BMS AFE, that is ISL 78714 or 716, comes with lot of built-in functional safety. So it can identify if a wire is cut. That could be one of the simplest stuff that can stop a cell from charging. Like one of the positive or negative terminals of the battery cell may be cut. That will be identified by the device, and it will be notified exactly which cell in which stack has got this problem. Or if particular cell is not at all catching up on the charging, or it is always on the low on the charge, it will also be notified to the user through the microcontroller. So that way, the total polling of, as I explained in my previous question, the total devices that can be daisy chained is around 30, and all the 30 devices of polling of all the data, including cell voltages, cell temperature, the current that is flowing, all of this data will be polled in every 10 milliseconds. So that way, every 10 milliseconds, the microcontroller and hence the user will get this data, and the decisions can be made based on that.
Okay. So now moving on to the next one, Mr. Sunil Deshmukh has asked how Renesas can help for thermal management in BMS.
Okay, so the device that is the ISL 78714 comes with 4 temperature measurement ports, apart from 2 other the IO ports. So the 4 of these thermistors, like for example, for 14 cells, if connected to one particular AFE, you have 4 temperature monitoring ports. You can connect your the NTC or the PTC to it, and then you can monitor the temperature, and that will be reported back to the microcontroller in the 10 millisecond polling I said, and that will be monitored by the this one. And in our newer devices, we are adding many more ports of connection to the thermal monitors, and then you can monitor the temperature very effectively, and you can make decisions. You can reduce the current that is flowing from the the BMS, or you can shut down, or you can reduce the load, which may be basically you are informing the motor driver to come down on the torque. Many such actions can be taken basically based on this one, and many more actions are possible. For example, you can put a gas sensor inside it. You can put a stress sensor on the cells to see if there is any bulging effect. And there are people using the carbon dioxide sensors inside the cell packs, so that you identify if there is bulk of carbon dioxide getting released in case of a kind of an indicator for a catastrophe that is waiting. So all of these can be done, and they can be interfaced with the microcontrollers, and those can be indicated very effectively on your cluster or any display system.
Okay. And someone has anonymously asked, what is your take on AIS 156 requirements for BMS?
Yeah, so AIS 156 requirements basically talks about the entire BMS, but the AIS 156 also requires a lot of safety concepts being implemented by the microcontroller as well as the analog front end, which is the actual BMS IC. So whatever is being asked or even more is already available on our device. So it is functionally safe up to ASIL D. So the ASIL D requirements encompasses requirements of AIS 156 as well as more than that. And of course, this entire system, there are a lot of requirements in terms of barcoding, or there are the passive tags that need to be required. Something is postponed now. So all of these are the system building requirements as a whole system. But otherwise, our device complies to all the requirements of AIS 156 as the ICs that requires this kind of support to the end system builder.
Okay, great. So Srinivasan, with that, we have come to a conclusion of this session. While there are a lot of questions, which are still coming in, we've answered, I think, 10-15 questions. Do you think it will be better if we can one-on-one reply to these questions, via email, or you can connect with them at a later stage? Is that better?
Yes, that would be good. So let's please help send the questions to me.
Sure.
I will reply one-on-one, and we can explain it even more detail with some of the documents as well.
Sure.
And that would be great.
So all our attendees, thank you so much for all the questions. We've received almost close to 25 odd questions. Really appreciate, you guys, your enthusiasm. But obviously we are at a time now, and we answered most of them, but few we couldn't take. So please feel free to, while I have received some of these questions against your names and your details, we'll get back to you. In case some of you have asked something anonymously, you can just drop us an email and we will connect you with the Srinivasan and the team. Okay. And with that, I will just, Srinivasan, I'll quickly just, say the concluding thoughts.
Thank you. Thank you, Rohit.
So thanks for the insightful presentation, Srinivasan, and all the questions that you answered. I am sure, you must be out of breath with, all the questions and, all the enthusiastic participation that we've received. So with that, we've come to an end of today's session. I wanted to thank you all for joining us. I hope you enjoyed the session and found it useful. and really appreciate your inquisitiveness and your attention and all the questions. Like I said, I'll definitely be sharing all these questions with Srinivasan and the team. In case you mentioned something anonymously, please feel free to share your email address and or your details so that we can reply to you directly. And would request you to take a few minutes to share your feedback in the form that opens when you exit the session. Next, I wanted to thank Srinivasan for taking out the time for his busy schedule for this, and our partner Renesas Electronics India for supporting this session. And as I mentioned at the start of the session, I'm really pleased to inform you that we've launched Transport Utsav, a complete festival of transport that brings together truck owners and fleets who will be attending this event, alongside solution providers such as trucks, tire, lubricant, finance, insurance, engine, truck technology, and component companies who will be exhibiting. We are organizing this exhibition in association with Nalagarh Truck Operator Union, which is Asia's biggest transport union. And this two-day event will take place on 3rd and 4th of March in 2023. So if this is of interest, do feel free to join us. In the meantime, here is a goodbye from all of us at CVF and TWF and the Renaissance team. Thank you everybody for joining in today. Thank you.